Phosphoric acid is a triprotic acid that undergoes 3 dissociations with 3 respective pKa values, shown here. With each hydrogen removed, the molecule gains negative charges, and therefore the electrostatic repulsion increases, making the conjugate base progressively less stable. As a result, the respective acids become weaker, reflected in the higher pK values. In the first dissociation, a proton is removed from phosphoric acid, forming its conjugate base, dihydrogen phosphate. Titration with sodium hydroxide solution is used to dissociate the phosphoric acid. The hydroxide anion removes a hydrogen, creating water and dihydrogen phosphate. As represented by the Henderson-Hasselbalch equation, dihydrogen phosphate and phosphoric acid are in equal concentrations when the pH is equal to its pK1 value of 2.2. Graphically, this is represented by the flat region of the titration curve called the midpoint, where 50% of phosphoric acid has been deprotonated. Further addition of sodium hydroxide causes the deprotonation of the remaining phosphoric acid, ending the first dissociation.
As with all titrations of polyprotic acids, the most strongly acidic proton dissociates completely before the dissociation of the weaker acid begins. As the pH increases further, the deprotonation of the resultant dihydrogen phosphate begins, producing hydrogen phosphate and a proton. The first endpoint now shown indicates that all phosphoric acid has completely dissociated. Sodium hydroxide now deprotonates dihydrogen phosphate to produce hydrogen phosphate and water. The concentrations of dihydrogen phosphate and hydrogen phosphate are equal when the pH is equal to 7.2, shown as the second midpoint. With continued addition of the sodium hydroxide, the remaining dihydrogen phosphate gets dissociated.
We now enter into the third dissociation, in which hydrogen phosphate is deprotonated to produce phosphate. The second endpoint is shown as we transition into the final dissociation. In a lab setting, an endpoint would be indicated by a color change of the selective pH indicator, in this case, thymolphthalene. Sodium hydroxide is being used to dissociate hydrogen phosphate. At the midpoint, the concentrations of hydrogen phosphate and phosphate are equal when the pH reaches 12.7, as shown in the graph above. The dissociation continues to deprotonate hydrogen phosphate until only phosphate remains, representing the third endpoint. During the overall dissociation, the solution resists changes in pH. This is because the added sodium hydroxide accepts protons from the acid and becomes neutralized.